Torch, digamma. Description. The torch, digamma function computes the digamma function, also known as the psi function of a given input tensor. The digamma function is the derivative of the natural logarithm of the gamma function. It is a special mathematical function that is used in various fields such as statistics, probability, and quantum mechanics. Inputs. Input: a tensor containing the input values for which the digamma function needs to be calculated. The input tensor can have any shape and data type supported by P-torch. Outputs. Output: a tensor with the same shape as the input tensor, containing the digamma function values calculated for each element of the input tensor. Steps. The torch, digamma function calculates the digamma function for each element of the input tensor. The function uses a numerical approximation method to calculate the digamma function values. Challenges and fixes. Challenge 1: input values near 0 are negative values. Sample use case: calculating the digamma function for a tensor containing values close to 0 or negative values might result in numerical instability and produce incorrect results. Fixes: ensure that the input tensor contains only positive values. If necessary, use a suitable transformation or check for values near 0 or negative values and handle them accordingly. Challenge 2: input values with high magnitude. Sample use case: calculating the digamma function for a tensor containing values with very high magnitude might lead to overflow errors or inaccurate results due to the limitations of numerical precision. Fixes: consider scaling the input values to a smaller range if possible. Use a stable numerical approximation method specifically designed for high magnitude inputs. Torch, special.xp2. Description. This function calculates the exponential of the given input tensor with base 2 element-wise. In other words, it calculates 2 raised to the power of each element in the input tensor. Inputs. Input: the input tensor whose elements are the exponents for base 2. The input can be a tensor of any shape and containing any numeric data type supported by P-torch. Outputs. Output: a tensor with the same shape as the input tensor, containing the element-wise exponentiation with base 2. The data type of the output tensor is the same as the input tensor. Steps. For each element in the input tensor, the function calculates 2 raised to the power of that element. The calculated values are stored in a new tensor with the same shape as the input tensor. Challenges and fixes. Challenge 1: handling large input values when the input values are very large. The resulting exponentiation might lead to numerical overflow, i.e., the result becomes too large to be represented as a finite number. Sample use case. Input tensor torch, tensor 1000. Output tensor torch, special.xp2 input tensor. Fixes. Use a different base for exponentiation, such as base A using the torch.xp function if the input values are very large. Apply a scaling factor to the input values before exponentiation to avoid overflow. Use the torch, special, expm1 function to compute x1, which can be more numerically stable for small values of x. Challenge 2: handling negative input values if the input values are negative. The resulting exponentiation will be a very small positive number. This might lead to numerical underflow, i.e., the result becomes too small to be represented as a non-zero number. Sample use case. Input tensor torch, tensor 1000. Output tensor torch, special.xp2 input tensor. Fixes. Use the torch, special, expm1 function to compute x1, which can be more numerically stable for small values of x. Apply a scaling factor to the input values before exponentiation to avoid underflow. If possible, reframe the problem to avoid using negative input values. Challenge 3. Handling complex input values. The express2 function is not defined for complex numbers. If the input tensor contains complex numbers, an error will be raised. Sample use case. Input tensor torch, tensor 11J. Output tensor torch, special.xp2 input tensor. Fixes. Use a different function for calculating the exponential of complex numbers, such as torch.xp. Convert the complex input values to real numbers before using express2. Challenge 4. Handling non not a number values in the input. If the input tensor contains non values, the output tensor will also contain non values at the corresponding positions. Sample use case. Input tensor torch, tensor float none. Output tensor torch, special.xp2 input tensor. Fixes. Replace non values in the input tensor with a valid value before using express2. Handle non values in the output tensor appropriately, for example by replacing them with 0. Challenge 5. Handling INF infinity values in the input. If the input tensor contains INF values, the output tensor will also contain INF values at the corresponding positions. Sample use case. Input tensor torch, tensor float and F. Output tensor torch, special.xp2 input tensor. Fixes. Replace INF values in the input tensor with a valid value before using express2. Handle INF values in the output tensor appropriately, for example by replacing them with a very large number or by raising an exception. Torch, EXPM1. Description. Calculates the exponential of the given input tensor element y-1. Inputs. Input a tensor of any shape containing the input values for which to calculate EXPx1. Outputs. Output a tensor of the same shape as the input, containing the element-wise calculated values of EXPx1. Steps. The input tensor is passed to the EXPM1 function. For each element in the input tensor, the function calculates EXPx1, where x is the element value. The resulting values are stored in a new tensor of the same shape as the input tensor. Challenges and fixes. Challenge 1. Overflow. If the input value is too large, the exponential function might overflow, resulting in an infinite value. Sample use case. Calculating EXPM1 of a very large value, like 1000. Fixes. Use a smaller input value to avoid overflow. Consider using a different function, like torch.xp, if the input values are too large. Challenge 2. Underflow. If the input value is too small, the exponential function might underflow, resulting in a value of 0. Sample use case. Calculating EXPM1 of a very small value, like -1000. Fixes. Use a larger input value to avoid underflow. Consider using a different function, like torch.log1p, if the input values are too small. Torch, special, EXPM1. Description. Calculates the exponential of the given input tensor -1. This function is designed to provide more accurate results for small input values compared to directly calculating torch, exp input 1. Inputs. Input a tensor containing the input values. The tensor can be of any numeric D-type. Outputs. Output a tensor of the same shape and D-type as the input tensor, containing the exponential of the input values -1. Steps. The expm1 function calculates the exponential of each element in the input tensor. It then subtracts 1 from each calculated exponential value. Challenges and fixes. Challenge 1: overflow when the input values are very large. Calculating the exponential can lead to overflow errors. Sample use case calculating torch. EXPM 11000. Fixes. The torch special EXPM1 function is designed to handle large input values gracefully and avoid overflow issues. Challenge 2: underflow when the input values are very small. Calculating the exponential -1 can lead to underflow errors. Sample use case calculating torch. EXPM1 1000. Fixes. The torch special EXPM1 function handles underflow by returning the result as 0.